Hi, Prof. I think we can start at 8:01 while we wait for a few more participants to come in.
Yes, so you just give me the signal that it's okay to start.
Okay. Okay, Prof. For those in this call currently, if you have any questions, please feel free to put it in the chat, and Prof will answer to your questions after his presentation. Thank you.
Actually, you know what? I'll be monitoring the chat, so luckily I have two screens, so I can keep an eye. So if you have any questions, feel free to ask them at any moment, and I will try to answer them at the appropriate time, even during the talk, because overall it's much more fun when there is some interaction with the audience rather than me narrating for 45 minutes.
Okay, Prof. I think we are good to go. We can start.
Okay, wonderful. All right, so shall I begin?
All right, let's go.
Great. All right. Good evening, everyone, and thank you so much for tuning in to another session of this event. And today I am giving another talk. And first, a disclaimer. So initially, that talk was supposed to be given by Georgia Perla, who is an amazing PhD student working with me on the topic of today's presentation. But unfortunately, George is unwell, so I had to take over. But I fully acknowledge that the slides are by him, and also research is spearheaded by him. Yet I'm obviously happy to answer any questions that you have about this line of work and this research. So today, the talk is, I will try to keep it quite high level, but still it's going to be slightly more technical than, let's say, the talk that I've given yesterday on smart contracts. And with that, please let me begin. So the title of today's talk is Practical Formal Methods for Distributed Systems. And obviously, many of you might have heard about formal methods, and obviously many of you care about distributed systems and getting them right. So these are very wide areas. So, and this talk is going to be a reasonably high level, and I hope to give you sufficient intuition to understand the main problems that the field of applying formal methods to distributed systems faces, and how we can solve this problem now or in the near term future. Now, hopefully we are all on the same page about what exactly we mean by formal methods. And by those, we mean a way to mathematically rigorously reason about the behavior of our software to provide guarantees that are backed not just by our intuition, but rather by mathematical proof, or even better, computer check mathematical proofs that our systems do what exactly what they are supposed to do. And this is actually where the state of the art is. So now there is a lot of interest in doing formal mathematics with the help of the computer that either constructs the proofs of mathematical facts for you automatically, or if it's not possible, assist you in checking that all your mathematical inference is correct. Okay, so that's going to be all about the formal methods. So the key focus of today's talk is on the practicality of those formal methods, especially in applications to distributed system. And this is our concern. So sure, in theory, we can build mathematical models of distributed systems, and people were doing it since 70s. So since Lampert essentially started to advance this area very early in the days. But what methods are practical for this task? So what methods could be useful for the engineers? Okay, so feel free to interrupt me at any point. I'm monitoring the chat here, so but also if you want to speak up, because I think it's much more fun to have this session interactive, and I also will be happy to answer the questions. So it's easy to actually clarify those concepts as we go along rather than at the end. All right, so let's talk about the practicality. So we are trying to build high-level trust and high-level assurance in our distributed systems. And when we want to have some guarantee that the system will build have certain properties, such that, for example, our blockchain protocols, they do progress by building the blockchain. They are not thwarted by a certain number of adversarial parties and things like that. So, and what are the effective and practical ways to do that, to build this assurance? So I'm going to answer this question indirectly by answering a related question, which is what methods for building assurance are most likely going to be adopted by practitioners in industry. And well, okay, so businesses are very practical. So like methods that are very expensive or take a long time to deploy and adapt for the practices, they are not going to fly. So which techniques are likely going to be used or are being used nowadays in industry in order to validate distributed systems? Okay, so hopefully with this, I have your interest and you get my motivation. So, and I think what we see is the following trend. So businesses like blockchain startups and large companies like Google, Facebook, sorry, Meta, Amazon, they care a lot about productivity. And actually, they care even more about productivity than they care about the correctness of the software that they build. Therefore, if formal methods are to be widely adopted in industry, the main sale point has to be that they make it easier for engineers to do their jobs, not harder. And the formal methods increase productivity. Okay, so any assurance of correctness is not a primary concern. So what do I mean by that? Well, some engineers actually have the job of ensuring that the systems they build satisfy certain correctness guarantees. For instance, this is the case for regulated fields. So engineers that work on software for road vehicles or airborne systems or medical devices, something that is really, really like critically, like should be really correct, and this is critical, have, well, I'm not really a lawyer, but as far as I understand, they have legal obligations to follow certain techniques and standards that ensure that the systems they build satisfy the required safety properties. So here I list actually some of the standards. So unsurprisingly, formal methods are widely used in these correctness critical domains, which are very few, because they are in effect required for the engineers to be able to do this job and, well, for people to like maintain their health and life after all. Okay, so but formal methods are not that widely adopted in software in general. So like companies like Amazon and Apple and whoever builds MongoDB. So they are using some formal methods, but not as much as they could. So because they are in effect required. So the reason for that is because methods actually not required, and most software is not really safety critical in this sense. So, and if we want to persuade engineers at large that the work of this kind of software should be also validated, we are not going to persuade them by saying, well, your software must be correct. They're just not convinced because, well, it might have bugs and those bugs might be fixed, and it's not like lives of many people and wealth of many people immediately depends on that. So correctness is a factor they indeed consider. You can ship systems that are just completely broken, but ensuring full correctness, like entire freedom from the bugs, is not really main concerns. More often, engineers, they care about shipping features very quickly or being able to quickly iterate and validate potential designs and refine them. So these are more typical commercial constraints. I think we can all agree with that. So in answering these concerns, I think is the key to make informal methods more useful in industry and adopted in practice. Okay, no any disagreement on this. All right, so and here's the evidence for this view. If we look at what kind of methods are adopted in industry, we see almost without the exception what you might call lightweight formal methods, like static analysis, model-based testing and monitoring, and even randomized testing of distributed systems. So, the common factor between these methods is the following one. They all require relatively little human insight to use. So in fact, well, okay, if you're already a software engineer, you probably know how to write tests, and there's nothing particularly new you need to learn to do that. And they don't need people in the loop to manually write additional artifacts. Like you write your code and then you write proofs about it, which is a completely not starter for adoption. Why would you write some additional stuff for something that already runs and can be deployed? And crucially, these practices like static analysis and random testing and whatnot, they all fit within existing software development workflows. They don't force engineers to fundamentally change what they are doing. So, and interestingly, so all these methods are used not exactly for proving the ultimate correctness of our software. They are used for bug finding. So not verification. So while static analysis, something that extracts the property of your code, can be theoretically used for verification, in practice, it's mostly used for finding bugs. So all these techniques are in fact like essentially fancy testing techniques, which is I think the key reason why they have been successful in industry. So testing and bug finding are big parts of engineers' job. So we want, like, engineers really like naturally want to find bugs, and these techniques help engineers to do job more effectively and with very little human effort. So it's very easy to convince engineers to write tests because they see the effect right away, and the cost of adoption is really, really low. Okay, so and indeed, people with experience in industry who also care about correctness and formal methods, they made the same observation. So if formal methods based on mathematical proofs are to be widely adopted in industry, they need to be and they need to behave like testing. So, for example, in this manuscript from the last year, Alistair Reid, who reads the formal method team at Google, interviewed a number of Google engineers, and they all saw that these engineers are very skeptical to formal methods for the reasons that I mentioned earlier. So specifically the reasons that in many cases developers simply do not see formal methods relating to this work. So they seem to address concerns that these developers actually don't have, or like the concerns that all the concerns can be solved with testing. And the second reason for skepticism is that even for the methods that do fit within an engineer worker's possibility, there is too much effort in adopting them. So developers thought that the effort actually wasn't worth it. So given that, and this is how the developers think, it's not surprising that the only methods that have impact in industry are so far lightweight methods that are more like testing than verification for the complete absence of the bugs. So this clearly address developers' concerns, and because they are lightweight, they have a good cost-benefit ratio. So indeed, the thesis of this work is that if we want to increase the adoption of formal methods by, as they say, 2 orders of magnitude, then we need to make these methods, even verification methods, be more like testing and fit the existing software development lifecycle. All right, so, and actually it's not just Alistair Reid who is a practitioner. So here's another big name in formal verification. So Peter Horn, who who used to be in Facebook/Meta until recently, but now he left to another startup that works, I think it's called Lacework, that builds security critical software. So even he came to the same conclusion as the practitioners. So his argument is that to scale the impact of formal methods, it is necessary to integrate them in the iterative, continuous model of software development that is now predominant in industry. So he actually calls it with a very catchy name. He calls it continuous reasoning as the formal methods equivalent of the continuous integration that we all know, the software development pattern, which is now widespread in industry. Okay, so let's zoom out a little bit and collect our thoughts to see how we can add formal methods in the flavor similar that is testing. So why testing is practical? Well, the biggest reason why it's practical because, well, testing is essentially follows the ideology of pay as you go. Namely, you can do as much or as little testing as you want. You might want not have tests at all. So for instance, if you focus at the moment, focus at the moment is to ship the feature you are working on very quickly, you can write some simple tests and ship the feature. But later on, when things are less busy and you are about to like release the second version, you can write more tests to build more assurance in the system. And like in order to ship, it's not required for you to have too many tests. So this is actually very, very attractive when correctness is not your main goal. And this is why like lots of web development actually assumes like very little testing. So because testing has this incremental flavor to it, you can fine tune the amount of effort you put in to get exactly as much assurance as you need. So that's the first reason why testing is practical and popular. So the second reason is testing is fully automated. So there is some initial effort involved into writing the tests, but once they are written, well, you really don't have to do much. So you can execute them without any effort. And even if the system changes, you very rarely need to change the test. So automation makes writing tests a very attractive proposition. If you have one-time effort, but exact consistent effort benefit from it, then even if software evolves and change, then well, that's a good deal. So clearly people would do a lot less testing if it wasn't so easily automated. So finally, the reason why testing is popular is it fits very well with existing software development workflow. So you can do test-driven development. So you can write tests first or write tests after you write the software, and everything is well integrated into your IDE like Eclipse or IntelliJ or VS Code. And the continuous integration systems runs the full test suite at every commit. So you don't even have to do anything. So you just push your code to the repository and the tests are run automatically. So testing is great. It makes a lot of sense. So unsurprisingly, most of the formal methods are exactly the opposite of this. So they are not pay as you go. So particularly the methods that offer you the super high assurance of correctness, such as interactive theorem proving, require very significant effort on the orders of months to years to obtain any assurance at all. So they are a very opposite of pay as you go. So you have to work for months until you actually benefit. And it's kind of all or nothing, because if you haven't finished your proofs, there might still be like a flaw in your reason, like at the part which you haven't finished, and you may claim no guarantees whatsoever. So yeah, that's why this is actually not super great. So also many methods are not automated. So they involve manual proofs and therefore constant effort to maintain the proofs as the code changes. This is actually a big challenge recognized by the community. So like changing the code is difficult enough, but now you, in addition to the code, you also need to change your proofs about this code. And this is not feasible in the typical commercial setting. And finally, formal methods are usually not well integrated with existing flows. So tests are usually written in the same language that you write your software, but formal methods require developers to learn absolutely different tool chains, such as the Coq Proof Assistant or TLA Plus, and use different development environments, which are usually developed in academia, so they are not as polished as let's say VS Code or IntelliJ. So moreover, because of this language mismatch between the formal methods tools and systems languages, as well as the lack of automation, current methods tend to be incompatible with software evolution. They really don't handle it well. So interestingly, as far as I can tell, all methods that we have seen adoption industry have at least one of these characteristics, but still, well, some other things have been done right enough, so the effort has been lowered. Okay, so the big outcome of this rather high-level part of this talk is that practical formal methods should be and are like testing. There should be incremental, pay as you go, and it should be automated. So essentially, push the button. So with that, I'm going to transition to actually tell you slightly more technical details about what exactly is the state of the art in formal methods, and why, despite all these bad things that I've just propounded, I'm kind of optimistic about the ultimate success of adoption of formal methods, even though, and specifically for distributed systems, even though we are not quite yet there as the community and like the humanity doesn't use formal methods as widely as the testing. By the way, this is maybe a good moment for me to pause for a minute and see if there are any questions. So feel free to ask something in the chat or unmute yourself and ask them in Zoom. Okay. Is anyone here? It's kind of hard to say. Hi, Moi. Good to see you. All right. No questions so far?
No, Prof.
Okay, good. All right, so let me carry on. So let's talk about the state of the art in formal methods. So okay, so now I will go slightly more technical. And just to reiterate, like, okay, no one, I was kind of asking that people might, I was hoping that someone would ask me, like, why exactly the formality is needed? So why actually we still care about that? So why do we need formal methods? Well, this is, why do we need formal methods that operate on precise descriptions of the systems and provide precise guarantee? So, and the formal answer to that, well, formality is precision. So this is exactly what helps you to uncover errors. So this is really clear in the case of the main topic of this talk, which is distributed protocols and distributed systems, where informal reasoning is difficult and more often than you think is actually wrong. So so George did a fantastic work compiling this particular table of errors in published distributed protocols. So pretty much all these are the protocols that you have used indirectly in one way or another without even knowing this. So this is what backs Amazon infrastructure. This is what backs the blockchain structure. And guess what? So people actually come up with the logic of this protocol, and more often than not, that that logic is wrong. And this is our way to show in a quantifiable way that this is why we need the formality and this is why we need precision. So, like, surprisingly, even for well-known protocol from distinguished authors such as Leslie Lamport, who is like the father of distributed computing and is a fantastic speaker, by the way. So if you look at YouTube for look on YouTube for Leslie Lamport lectures, I think you will have like a lot of fun. So he's a like a really nice presenter. Okay, so like even from him, the published protocols, they have errors and sometimes quite severe errors. So if we deploy that in production, that might lead to catastrophic loss of data and, well, money. So the other answer, which is less obvious why we call about formal methods, is that formality surprisingly might enable some automation, which is the key to making methods practical, but that's also like the point that requires further elaboration. So we will get back to that later. Okay, so hopefully this table, which by the way is available on GitHub, I will give you a link if you're interested, if you get in touch, and you're welcome to contribute to it with pull requests. So this table should be like a convincing enough argument that we should really care about formal methods and application of distributed systems. Okay, so how can we build assurance in distributed systems? And what are the different techniques that allow us to do that? So we can divide these techniques into two classes. So the one technique, which is familiar to probably many of you, are the testing techniques, which check the properties by execution. So they run the program and check that certain properties are preserved as the program executes. And there is also kind of the large spectrum of verification techniques, such as interactive verification, semi-automated verification, and automated verification. And here, left to right, I ordered them according to the amount of involvement of the programmer that they require. So verification techniques provide much stronger guarantees because they don't just reason about individual executions of your system, but they actually reason about all possible scenarios in which your system might occur. So my goal is to explain that these techniques, explaining this technique in detail. So okay, I'm actually not going to explain these techniques in detail, but I will try to give you sufficient context to understand the benefits and disadvantages of each approach in this spectrum, and particularly how some of the disadvantages might be alleviated, and we already have all the right tools for that. All right. So let's talk briefly about testing and model checking. So testing is all, as we all know about. So model checking is that sounds more fancy, but in fact, while sometimes these are understood as different things, they are very similar. So model checking in practice being mostly just systematic testing. So instead of testing particular scenarios, we are trying to cover like certain subset of behaviors of our program in a systematic way. So the idea is that we are given some kind of precise description of the system, maybe even the implementation of it. And this could be either, okay, so that might be implementation in some normal programming language like Java, C, Go, Rust, whatever, or some sort of abstract specification expressed in the modeling language, which is not something that we would deploy in production, but something that mimics very precisely the important parts of the logic of our system. So, and I also have a precise description of the properties we want to check, such as our distributed system never goes down, or even if less than the third of the nodes crash, the consensus still can be reached in our protocol. There is quite a bit of variation in terms of how properties are described, but common ways include some input pairs for the behavior of the system, some properties of the traces that the system generates as execute, as well as logical assertions in something like first order logic or linear temporal logic that tell you that first we can see this event happening in the system, and then we can have that event happen in the system in exactly this order, but not another way around. So when given these two things, we can execute the system and check that execution of the system satisfies these properties. Okay, so to make things slightly more concrete, here is an example of model checking or systematic testing of a system's model. So here we're actually, what you're seeing, you don't need to read all this code, but I'm just going to tell you that this is a specification of one of the simplest distributed consensus protocols, which is called two-phase commit. So Leslie Lamport likes to compare it with a very progressive wedding, when instead of just the bride and the groom, we have multiple brides and multiple grooms, and they all need to say yes in order to commit the wedding transaction, and if at least one of them says no, then the whole thing is rolled back. So this is what the two-phase commit is about in very informal terms. But obviously, this is something that's used widely in distributed systems implementation as a part of more complex protocols. Okay, so this is where, like, this is actually very concise description of this protocol in a modeling language. So this is not a practical language. This is a language for modeling and describes in the high-level details of the system called TLA+, which also unsurprisingly developed by Lamport. So the idea of the protocol is actually captured just in this few many lines of code. And the property we are interested, shown in the top right corner of the slide, says that, well, we cannot have the state in which some of the parties said that they abort the transaction and some say that they committed the transaction. So they all either abort together or they commit together. So and this actually means the consistent state of the system. So we always want the distributed parties, or all brooms and brides, all grooms and brides in the system to be in a consistent, to hold the same decision. Okay, so now how do we build an assurance that this property indeed holds over this specification of the model? So, okay, so you can kind of read the model and try to convince yourself, but we can be slightly more systematic and test it using the model checking approach. So a model checking approach actually works in a very elegant way. So first, it sees what is the initial state in which our systems can start executing. So this is basically like what happens when you just deployed the system. And starting from the initial states, it is specified by this TP init equality in blue. We can apply all the possible transitions that tell how the system can evolve by the parties communicating with each other, sending messages and changing their state. So for example, the TP next, which is shown in green, shows how shows all the variety of transitions that the systems might make. So now having this definition of the initial state and what can happen next, well, the system is non-deterministic, so it can actually change in multiple possible ways. But what model checking gives us is a systematic way to start enumerating all the states according to this transition, and for each state, we are going to check this property, the transaction commit is consistent, which one, the property that we have on the right. So, and if this holds, then it's great. And that means that we have tested certain subsets of the states in which the system might be, or even better, if that doesn't hold, that we found a bug. And this bug is going to be stated in very concrete terms. So because we can now see exactly how we came to the state that violates our property. So this is pretty important. So this is called safety property, and checking it this way gives us some assurance, but not a complete one, that either something is wrong with our system or nothing goes wrong up to certain finite number of steps. So since this system has infinitely many states, we're only going to check a subset of those, but we are going to construct this subset systematically. So that still gives us reasonable assurance guarantee. So now you can see how model checking is essentially like fancy testing. That's actually a good question to a good moment to ask questions. And I see that, okay, so Aditya says hi. I'm not sure if it's going to be followed by a question or it's just hi. So hi, Aditya. Yep, happy to take any questions at this point. No questions. Okay, this is promising or not, I'm not sure. Okay, but anyways, so hopefully, since there are no questions, everyone has either tuned out and is enjoying the Friday evening, or still with me and is about to learn about how model checking is used in practice. So let's get to that. So model checking and TLA Plus has been extremely, okay, not maybe extremely, but reasonably successful in industry by the measures of an academic tool. For example, Amazon Web Services has a division that uses TLA Plus, the same language that I've shown you on the previous slide, to validate systems designs for their cloud products. And also they do something a bit different, where instead of the model, they use the reference implementation. So in fact, like instead of the model in the different language, they have a model in the same language. So for example, they have two implementations of the same distributed file system, both written in Rust, one of which is very simple and doesn't use any features, and this is not something that goes to production. So this is just as a reference for the developers to keep an eye on. And there is another that uses all the advanced features. So it uses concurrency, it has lots of optimization. And then what they do at Amazon, they use the reference implementation to validate the behavior of the real implementations. They kind of show that these two things, they execute consistently in lockstep, and there is always a correspondence. And there was actually a paper published at SOSP, a very prestigious operating system conference, just about doing this approach, which works amazingly well. So MongoDB does real-time conformance monitoring. So as the system runs, it collects logs, traces of execution, and when in the real time, these traces are checked by the TLC model checker, so which is a part of the TLA plus suite, and make sure that the implementation behaves in the way it was designed and understood to behave and expressed in terms of this high level model in the modeling language. So, and if it isn't, then an engineer is alerted to take a closer look. So finally, Apple has a database product called FoundationDB, and their software is designed such a way that can be run not in the production mode, but sort of like in a simulator. So the simulator can decide what happens, and can do something very similar to model checking. So they do this exhaustive random test that is biased by annotation in the source code to explore paths that are more likely to have errors where something iffy can happen. All this works very well. It's lightweight and it works exactly like testing. Well, it is testing, so it's widely used in industry, except it's slightly more systematic testing. So what's the problem with that? Well, the problem is that it's incomplete. Okay, and this is something that I'm going to show by this fancy Venn diagram. So the problem is that it doesn't get us as far as we would like to have. So remember that the essence of this method is that we explore executions of the systems and check that these executions are safe. And the problem is that most of the systems that you care about have an infinite number of executions, and executions can be infinitely long in time and the number of steps that they make. So we will never be able to explore all of them. Bummer. So testing in this sense is useful but incomplete. It can never establish the safety saying that there are no bugs for infinite state systems. So like, for example, you could consider the reachable states. And what we want to show is that all the reachable states in our system is actually a subset of the state states. But the system shows you only parts of the reachable state. So and the pack doesn't really prove that all your reachable states are strictly speaking the subset of the states, the safe states. So you can imagine a situation where this green cloud actually sticks outside of the pentagon, and we don't manage to detect it because we didn't explore those reachable states that stick out. So yeah, so can we do we need to do better? And I think so. But in reality, even very popular, well-tested systems are full of critical bugs just because of this incompleteness. So bug. Okay, so my headphones have a bug, so occasionally they switch off. Can someone please indicate that you can still hear me? Because I heard the beep and I tried to rectify that. So someone please signal. It's okay. Good. Okay, so then I carry on. Okay, so what can we do? Okay, we can do what's called interactive verification. While this, there's a lot to say about verification, it's a huge area. In its core, it's actually a very simple thing. So verification is an art of building over approximations, or in different terms, establishing abstractions. So recall what we are actually trying to do here. So in the conceptually, we are trying to do something very simple. We are trying to show that all the set states in which our system might end up being, which obviously we cannot compute all because there are infinitely many of them, is still a subset of the states which we consider safe. And this is kind of a little bit philosophical because there might be states that our system can never encounter, but our safety property is still defined on those states. So they're just platonically exist somewhere, but this is not something that we can actually see by executing our system. So this state, all the states of our systems should fall in the subset of safe states. So, and the problem is again that we cannot compute even the green set. This cloud set is it's not it's infinite. So how can we establish this inclusion properly? Well, mathematics is all about reason about infinite sets. So in general, we cannot using the methods such as testing, but in this particular case, we can. So if we can show that from every safe state, if we take a transition as the system prescribes, we will always reach another safe state. Then the state of safe states is an over approximation of the set of the states that are reachable by the system. So let it sink for a second. So therefore, if we show that every state of the system, so if we show that every safe state basically transitions to another safe state, and the system always starts from the safe state, then we know that the set of all safe states over approximates the set of all reachable states in the system. So we show exactly what this diagram shown. So, and this technique, actually, this proof technique has the name. So if you're familiar with the term, which you might be, this is called finding an inductive invariant of the system. So formulating our property in a way that if it holds in the initial state of the system, it cannot be invalidated by the system making a step. And this is exactly like mathematical induction, if you remember this technique. So if something holds at the very beginning, and from each position over one step, it's still like in which it holds, make one step and it still holds, then it holds for all steps, for all reachable states. So this is what the inductivity is about. How does this ring work? So why does it allow us to build this over approximation? Well, suppose that there is a safe state, not necessarily a reachable one, and it's shown in yellow. So that transitions into unsafe state, which is shown in red. And well, there are two cases here. Either the yellow state is reachable or it isn't. And if it is not reachable, so this is not really the state in which our system cannot be, everything's fine. If it is reachable, however, then we've just shown that the safety is not an over approximation of the set of reachable state. In other words, we found the bug. So safety might look like that, and this is actually a bad case, but it doesn't look like that. So this actually means that our system is badly written or badly designed, so it actually is not safe. So there are states in it that do not fit into the universe, into the set of safe states. Okay, so inductively, so the idea is that inductivity is the idea of being closed under this transition relation. And this is the proof method to establish the over approximation. Okay, now here comes the twist. Almost no interest in safety properties are inductive. So this means that while there are some safe states, that there are some states that are safe, but they transition into unsafe states. So by what I mean, so you see, if we reason about safety property, we basically assume that we can take any state that is safe regardless of whether it's reachable or not. And so this red arrow at the top, it shows that we have started from a state that we assume is safe. We took one step according to the system definition, and we ended up outside of the safety property. So, and for that means we found counterexample to the induction, or CTI for sure. Okay, so what can we do to verify systems, and how inductivity is still a good thing? Okay, so our safety property might be not inductive, but what happens is that we actually can restrict it. So it's like we need to assume some extra things and restrict this over approximation until eventually it becomes inductive, until you see it still contains our all reachable states, and yet it is contained within the set of the safe states. And this is actually a little bit of a work of art. So you see, we want to find a property which in itself implies safety, so it's a subset of all safe states, but it's also large enough to contain our reachable states. So this is actually like not very trivial problem. It's kind of finding this balancing act which fits you precisely between these two shapes. Okay, so but now if we manage to find it, it's actually great. So that means that each reachable state is safe, and our property is within safety. So by this two-set inclusion, we know that we have the safety of the reachable system. So what's the problem with finding this inductive invariance as our main working horse for proven safety? Well, it's actually, I made it look very simple. The problem is, I've been showing you the shape of the sets and the shape of the reachable states and the shape of the states and so on. But in reality, we have actually very little idea about the shapes. So the problem is that we don't know what the whole set of reachable states look like, and we don't know what the whole set of safe states looks like. So that so when we are trying to verify a system, we really don't know the states. So the only thing we see is this inductivity property. Concretely, to verify a system, we come with a candidate invariant, some yellow property, and try to prove that it's inductive. So it's contained within the safety property. Some cases of the proof go through, but others typically do not. And when our proof doesn't go through, we have to rephrase our invariant and try again. So think of it like just making a different cut of this blue shape from the previous slide. So looking at this case that didn't go through, we have to imagine the shape of the different invariant clauses in our mind and identify what the problem might be and try to remedy it. And this is something that actually requires a lot of intuition. So this is challenging, like finding good inductive invariants is challenging in two ways. First, it's difficult to figure out what's going on. So to come up with an inductive invariant requires very deep understanding into the protocol works. So, and usually it's the designer of the protocol who can state these inductive invariants. And in this fact, this is how these protocols are usually proven safe on paper. But if you just prove things mathematically on paper, you can still make mistakes. So even the experienced researchers who develop protocols, they usually spend more time on distilling the inductive invariants for those protocols than actually formulating the logic of the protocol. So second, you have to write these proofs manually. And until recently, that was the state of the art. And this is challenging and quite frustrating because you can spend weeks on the proof, like exploring these like states, like proving this case, okay, it holds and holds, and then you have 20 something cases, and then this one doesn't hold. So, and you can spend weeks doing that just to learn that, well, your candidate invariant is actually not inductive, and you have to try the new shape. You have to try something from scratch. So to connect this with the beginning of the talk, interactive verification is the very opposite of practical so far, the way I present it. So it's not automated, and it's not pay as you go. It requires deep understanding of the protocol and a lot of effort until you find and establish an inductive invariant, and you have nothing to show for your effort. So again, it's not pay as you go. So it's entirely unsurprising that this is not really used in industry, at least outside of safety critical domains. But let's keep pushing. So maybe there is a way to salvage this method so it will become more practical. So there are actually ways to address this problem. So I'm trying to be optimistic in this talk. So I'm going to describe the way how we can address this impractical way to build inductive invariants to prove safety of our system. So the solution, of course, as we've seen, is automation. Here's some interesting parts. So semi-automated verification is something that still requires you to come up with invariants, but it doesn't require you to check them. So instead, the check-in of their validity of their inductivity happens automatically. So it alleviates the problem rather than fully solves it by assisting the human verifier in automated theorem prover. So that can typically handle some nitty-gritty details of the proofs of these individual errors, individual transition, but it still relies on human insight to provide the high-level structure of the proof. And however, semi-automated verification still has this problem of requiring people to guess the invariant. So to write it, which is a very creative process. So automated verification ideally completely eliminates the proof effort. So you only need to write your system description and the property that you care about, and somehow the invariants will be found for you. Although this comes at the expense of expressivity. If we want the proofs to be decidable, we have to be very careful with how we express our systems, and we are restricted in terms of which properties we can prove automatically. So this is actually one of the cornerstones of the theory of computer science. So there are very few problems for which we can always give a binary answer, yes or no. More frequently, we have computational problems for which we have no algorithm that will always terminate with an answer, yes or no. This is so known Haltian problem. And in other words, the logicians causes this decidability problem. But logicians in the last 30 years worked really hard, and they identified specification languages for which the decidability is actually, for which questions that you can phrase in them are decidable. So you can write a program that always terminates and gives you the answer yes or no. This property holds or the property doesn't hold. Okay, so still there's automation, and just as importantly, the existence of this automation for systems written in this very specific description languages and logics actually enables us to automate the process not of just checking the invariants, but even discovering them. Okay, so and in theory, we could completely eliminate the need for human insight in discovering this invariant. So the humans will only be needed to, well, define the system and define the properties that we care about. Okay, Let me try to speed up a little bit. Okay, so this is how the automated verification helps. So this is very wide field. And as we've seen, our problem with interactive verification that you lose a lot of time trying to prove inductive invariant that might be actually not inductive. And when your proof fails, you have to revise the invariant. So let's try to do better. So there's actually a tool called IB that does exactly that. So they realized that you can automate the process of refining invariant. How does it work? Well, we have the same two-phase commit protocol as before, for example, and we try to say, okay, this is invariant. This is actually something that holds over any transition. So this is how it's written in IB. So we want to establish the safety property, and we want to establish to show that by showing that it's inductive. But sadly, it isn't. Okay, I won't ask you to validate it, but this is because the proofs in the system automated. The fact of inductivity is not something that you need to prove manually. This is something the system can prove for you. So, and the tool can show you exactly why it fails to prove the inductivity. So it just shows you the essence of this red state. And if it tries to prove the inductivity of this property, it fails, and you have a counterexample. So here is the state on the top that shows that replica 1 is working and replica 0 is already committed. So it transitions into a new state that is at the bottom with replica 1 aborting the transaction. And now we have exactly the counterexample of this variant. And the problem is that the first state is safe and it is consistent, but the second one isn't. So the nice thing is that our invariant can be made inductive, and it isn't inductive in the first state. So we need to constrain our variant by adding another clause to it. And turns out that this clause is exactly what we need. So now we run it through the tool, and we can get something useful out of it. So let me show it more explicitly. So we have a safe state shown in yellow, and it transforms into an unsafe state. But well, this is actually yellow state, which is bogus. So it's safe, but this is not the state that belongs to the state space of our system. It's not within the green cloud. So it's not reachable. So now we need to make sure that this yellow state will never be considered. So we restrict our invariant. So now instead of the yellow pentagon, it will be kind of this more like blue shape. And the way we do it is by adding a clause to our invariant, so the one on the bottom. So that eliminates the state. And then we keep doing that. So the problem is that we still need to some insight in picking these restrictions and picking this clause. So the risk is if we do that very vigorously, and we do not correctly understand why the yellow state is unreachable, we might add the clause that makes our safety property, our invariant, too restrictive. And in fact, it now excludes some reachable state. So this is bad. So we could say that, oh, the state on the top is unreachable because our replicas never enter the working state. But this is not true. If our standard, we just eliminated a large number of reachable states. So that's pretty bad. And the problem now is that we are going to keep getting counterexamples to induction, such as this one. And if we keep adding clauses, there is no way we can get inductive invariant. So in fact, we are going to make it even more restrictive. So we only further and further restrict it. So there's a still insight required in coming up with this invariance, because if you just mindlessly add restrictions, you might up in infinite loop. Can we automate this process, you might ask? And the nice thing, yes, actually we can, with a lot of success. So this is optimistic talk, so I'm going to give you the rounds of my optimism. So there are many ways to automate it, and I'm going to show you some of them. So the first one is we can guess a clause and perform a bounded model check to validate our guess. Remember what model checking is. So it explores some finite number of states. And if in the finite number of steps we manage to see that we actually go outside of this blue shape, that it was bad shape, because it certainly doesn't cover all the reachable steps. So, okay, so we somehow need to enlarge it and reconsider it. And if we explore enough, so that works good, as long as you have the large bound for your model checking. Another method is actually even more clever. So recall that I've been showing you these shapes on the slides, but we don't actually know these shapes because these are infinite state systems and we are trying to verify. So even though we can automate the inductiveness proofs, that doesn't mean that we actually can enumerate all the sets. They are infinite. But one thing that we can do is to discover inductive invariants is we can artificially restrict the system so that it is finite. So, instead of kind of trying to come up with an invariant that covers all the infinite set of reachable states, we restrict our system. And for example, in two-phase commit, we can only consider scenarios that have 3 replicas and only 1 transaction. This is a finite system. There's only so many things it can do until it comes to a halt. So in this restriction, if we can enumerate all reachable states, and then we sorry, yeah, if we can enumerate all reachable states and the safe states and so on, we can like just check them one by one and try to see what properties holds for all of them. And this is again the property that only holds over a finite number of states. But now we can use a little bit of intuition and try to see if we can generalize it to show that it holds over infinite number of steps and a number of states. And this is what systems like I4 C3PO do. There's actually a system called C3PO. That's rather funny, I think. And they perform this guess and then generalization, and then they use the same machinery to check that the generalization is actually inductive. And finally, there is the way which utilizes some artificial intelligence in the loop. So, and the idea is that, well, as you recall, there is a risk that what was added would close the clause that is restricted the state space too much. So we actually would end up in something which is smaller than our state space, and thus that will eliminate some reachable state. But in fact, what we can do is just use it as a starting point. So, and we can go in this direction. So we start from something that is small, and we start adding like more and more disjuncts into our invariant until it covers the set of our reachable state. And again, at each iteration of this, what we do, we use the checker for inductivity to make sure that our invariant covers all the reachable state. And there are systems such, one of them is called dist AI, which I think is not a very good name because it doesn't tell much about the system, that do exactly this, and they actually use some clever machine learning to automate the search for this larger and larger invariants. Oof. Okay. So that has been a big tour de force of the methods. So now let me summarize why we should care about that. Well, we care about that because after all, we are after showing that the green cloud is within the yellow pentagon. Green cloud is our system. Yellow pentagon is the property that we care about. And unlike the testing here, if we show this inclusion, we are really, we are in a really good position because now we know that our system is safe, and this is something that the testing or model checking don't give to us. So this is why I'm quite excited about this line of work, and I'm working on it with George and my other PhD students. And so here are some limitations of the state of the art and some really interesting future work that we are building. So automated verification um, needs protocols expressed in certain decidable logic. So yeah, it's big problem. So, but if it's possible, but it is possible to express complex protocols such as multipaxos, so the state of the art indecidable fragment of first order logic, but it's super difficult. So it actually requires a lot of expertise, not just in distributed systems, but also in this logic. So, and it looks nothing like an implementation in C++ or Python or Go that you would implement. So, and there's absolutely hopeless that a qualified engineer without special logical training can do it in a reasonable time. It requires deep expertise that can come, that are required to come up with inductive invariant. So one question we are looking at is that, can we automate the translation of specifications from languages that the engineers already use, maybe not exactly Go or Rust, but something like TLA plus, into this decidable logic that allow for this automated inductive invariant check. And there's a lot there, and I think particularly, and we are particularly so this is actually particularly related to learning from finite instances. So we first try to see how the model behaves, and then we try to see what its definition would be in this weird logic. And there is some room for AI and machine learning involved. And the problem is actually in this form is really similar to automatically finding inductive invariance over something that is already in this logic, but somehow it hasn't been explored at all. So still, like, this is a very much niche area where people with expertise in this logic verify these protocols, and like practitioners don't really use it. So a different avenue is we now can like do automated verification of protocols, not just testing, but we still don't have a very good way to connect these protocols, which are abstract models of our distributed systems, to the actual runnable implementations of distributed systems, which are still riddled with bugs. So is there some way to leverage the decidable specification to make this possible? Maybe we can so maybe we can't automatically verify every aspect of the implementation, but in some way we can do this incrementally in a pay-as-you-go fashion by connecting the formal model using the monitors or approaches such as testing to our actual implementation. The final avenue that I want to mention is actually rather ambitious. So there is a lot of work in so-called program synthesis. So when you, instead of writing your code, you write some sort of specification of your code that you believe. And this is something that has been applied to tasks such as Excel flash fill. And okay, many of you might have seen GitHub Copilot, which is not exactly in the same vein because it more frequently definitely don't know that it produces junk, although it looks really, really cool. But imagine that we want to write a specification of protocol, and we actually some specification of the properties of the protocol we care about, and we want to synthesize the protocol. Since we can now reason automatically about distributed protocols, can we also construct those protocols automatically from the properties that this protocol should satisfy? So I give you a safety property. Can you automatically show me that the protocol that is useful and satisfies this property? So this is our big vision. This is our dream. And I think that will be really amazing. And with that, I think I'll stop. So thank you so much for your attention. And we still have a few minutes for questions.
Thanks, Prof, for the presentation. For those in the call, if you have any questions, please leave in the chat.
Okay, thanks for sharing. This is very new to me, have to digest. Sure, I'm happy to provide more pointers if you reach out. Or if you want to have something really entertaining, just look for Leslie Lamport on YouTube. So he's a way better speaker than me, and he gives great interest into formal reasoning about distributed systems in particular. Also, Leslie Lamport is the person who made Later, a truly remarkable guy. He has a Turing Award for all his contributions. All right. Seems like there are not that many questions, or none at all. I'll be happy to wrap it up now, but well, anyone is welcome to, and everyone is welcome to reach me out by email and follow up on that.
Thank you so much for your presentation, Prof. With that, I actually would like to ask for your permission if whether you'd be okay if the recording is to be uploaded.
Yes, absolutely.
All right, thank you so much. And for the participants still in the call, there will be a form that I'll be sending out soon. Please fill up your attendance, and Prof, back at you.
Okay, thank you so much. Take care and enjoy the rest of the event.